All right, welcome to the Explainer. Today, we're strapping in for a complete engineering teardown of the absolute most critical component in all of machine learning. Whether you're dealing with a basic image classifier or a massive language model, there is a fundamental core driving the whole shebang, and we're going to unpack exactly how it works.
So think about a model like GPT for a second. We throw terabytes of data at it, sure, but what actually forces the model to learn? I mean, what physically compels those billions of parameters to adapt and get smarter during training? It's not just the data itself, it's the engine of optimization.
And that engine? It's Cross-Entropy. You can think of me as your lead engineer today, and I want to be incredibly clear right up front. This isn't an arbitrary choice that developers just kind of stumbled upon. Cross-entropy is the mathematically optimal path for probabilistic classification. It's derived directly from the principles of maximum likelihood estimation. This is literally the engine of your neural network.
Okay, here's our blueprint for today's teardown. We're going to cover the false engine, visualizing learning, the logarithm penalty, the mathematical blueprint, the PyTorch API, and finally, a reality check. Let's get into it.
First up, the false engine. Mean squared error versus cross-entropy.
So let's dive right in. Back in the early days of pattern recognition, engineers actually tried to use mean squared error, or MSE, for classification tasks. But MSE failed miserably. Why? Well, because MSE assumes errors are Gaussian and linear. In classification, when you use a sigmoid or softmax activation, the outputs saturate. If the model was highly confident but completely wrong, the gradient, the actual signal telling the model to update, became tiny. The network essentially just stalled out. Cross-entropy completely fixes this by being mathematically tailored for nonlinear probabilities.
To really get the intuition behind this, imagine you're a telegraph operator. If you live in a desert where it's sunny 99% of the time, you'd create a highly efficient desert code with really short signals for sunshine. Low cost, right? But what happens if you move to rainy London and keep using that exact same desert code? You're constantly forced to use long, inefficient signals for rain. You're wasting bits. Cross-entropy is literally the measure of those wasted bits. It's the mathematical cost of using a flawed model to predict the real world.
Section 2, visualizing the learning process.
The absolutely crucial point here is understanding our target. In machine learning, the truth is usually represented as a one-hot vector. Mathematically speaking, it's a probability distribution where the correct class is a single, razor-sharp 1.0 spike, and absolutely every other possible class is exactly 0.
Now, what's really fascinating is how this gives us a visual definition of learning. You see the truth over there on the left, that sharp, perfect spike. But your model's initial prediction? It's usually this blurry, wide, unsure mound of probabilities. Learning is this beautiful, elastic process. The loss function grabs that blurry mound and aggressively pulls it, stretches it, and sharpens it until it perfectly mimics the shape of the truth spike.
Moving on to Section 3, the logarithm penalty.
Okay, here is the literal alarm bell of the network. This is the surprise curve. Y equals the negative log of x. Watch what happens as the probability, our x value, drops. As the model's assigned probability for the correct answer gets lower and lower, dropping below 0.1, you get this intense red warning glow as the plot aggressively shoots up toward infinity. This is the visual proof of why confident errors are so outrageously expensive for the model. The curve is incredibly steep right there.
Just to ground this in reality, let's look at a real metric. When the model's predicted probability for the correct class drops to just 10%, or 0.1, the loss shoots up to 2.3 nats. The sheer magnitude of this penalty is exactly what snaps the network out of its vanishing gradient stall and forces an immediate aggressive correction.
Section 4, the mathematical blueprint. So let's inspect the structural integrity of the math itself. The formula is the negative sum of p of x times the log of q of x. You can think of p of x as the ground's truth, our one-hot vector. Q of x is the model's prediction. By taking the logarithm of the predicted probability and multiplying it by the truth, we isolate the exact error. And that negative sign, that just ensures our final calculated loss is a positive number, since, the log of a fraction is always negative.
And right here is the true magic of this blueprint. When you calculate the gradient, the derivative of this loss with respect to the raw outputs, it simplifies to something unbelievably elegant. Predicted minus actual, y hat minus y. It's that simple. If you predicted 0.1, but the truth is 1, the gradient is negative 0.9. It aggressively yanks the model back on track. This perfect linearity is exactly what prevents the vanishing gradients that plagued our old friend mean-squared error.
Section 5. Demystifying the PyTorch API.
Let's see how all this math actually builds out in production code. We're going to demystify the black box right now. On the right, we have our standard mathematical formula. On the left, PyTorch's nn.CrossEntropyLoss. Notice how the log in our mathematical formula connects directly to the implicit log softmax operation happening under the hood in PyTorch. PyTorch intentionally fuses log softmax and negative log likelihood into one highly optimized, stable kernel.
But why do they fuse it? Well, it's because of 3 critical engineering failure modes on the GPU. Step 1 is the infamous log of 0 crash. If you manually run softmax and it rounds a tiny probability down to 0, the log of 0 goes to negative infinity, and boom, your training instantly crashes with nans. The fused kernel prevents this entirely. Step 2 is the double softmax. If you accidentally pass probabilities instead of raw linear logits into PyTorch's function, it completely squashes your gradients. And step 3 is class imbalance, where a model basically ignores minority classes just to cheat a low cross-entropy score. That's when you have to step in and use weighted penalties.
Finally, Section 6, the confident reality check. I want you to imagine a courtroom for a second. The truth is an established fact. The suspect wore a red hat. Now your model is a witness on the stand. If the witness says, I am 10% sure it was red, the judge is annoyed. But if the witness pounds the table and says, I am 100% sure it was blue, the judge's frustration shoots to infinity. That frustration, that's cross-entropy. It is the mathematical measurement of the cost of being wrong, heavily weighted by exactly how confident you are in your wrongness.
But this leaves us with a fascinating limitation. Standard cross-entropy treats all wrong answers exactly the same. If you show it a picture of a dog and it predicts cat, the penalty is identical to predicting car. But obviously, we know a cat is semantically way closer to a dog than a car is. So if cross-entropy treats all mistakes as equally terrible, how do we engineer a future loss function that actually understands context and nuance? Well, I'm going to leave you to ponder that one. Thanks for joining me on this explainer, and keep learning.